Okay, so here we go. 11.1, number 15. All right, this one. All right, so it says a disk with a radius of 0.25 meters. So here we go. Our radius is 0.25 meters. It's to be rotated like a merry-go-round through 800 radians. How should I label that 800 radians, you guys? Good, that's your delta theta, right? It's the angle that the merry-go-round or disk has turned through. It says it's gaining angular speed at the constant rate alpha through the first 400 radians. Oh, and then losing angular speed at a constant rate of negative alpha until it is again at rest. So this is a little bit misleading. So do you guys understand what's happening? There's one part where it's speeding up, so that's the first half of this 800, and then the second half it's slowing down and stopping again. Okay? So it's kind of symmetrical motion, right? It's speeding up and then slowing down. So I'm going to actually just change this to 400 radians, and let's just worry about the speeding up. All right? It says the magnitude of the centripetal acceleration of any point on the disk is to not exceed 400 meters per second squared. So our centripetal acceleration has got to always be less than 400 meters per second squared. All right. So Zach just said, wouldn't that be tangential acceleration? And I mean, the answer is no, because it says centripetal in the problem. So the idea, you guys, is...
I was just worrying about labeling, that's all.
Okay. Are you okay? Or
Yeah, I'm okay.
I mean, do you guys understand that the faster I spin this, the larger the centripetal acceleration of any point is? Right? Okay? So, what we want to do is we want to make sure that the centripetal acceleration never goes above this value. Okay? And so then the question wants to know what's the smallest possible time you could take for this to happen? All right, so first of all, can we agree that it's going to take the same amount of time to speed up as it is to slow back down? Yep. Does that make sense? Mm-hmm. All right, so the question then is what's the least time that we can use to get up to, to rotate through 400 radians, okay, with this condition? Well, so here's where that little trick comes in. So we learned just a minute ago that centripetal acceleration is omega squared times radius, right? Or you could have used this equation to solve for linear velocity at the outside edge, which would be the same thing. All right? So we need this to be less than 400 meters per second squared. So multiply both sides by the radius and take the square root, and I think you'll find that your angular velocity has got to be less than... why am I dumb? 40 radians per second. So the idea is if your angular velocity goes above 40 radians per second, then you're going to exceed that centripetal acceleration. Follow? All right. So we're talking about the speeding up part. So we can't, our final angular velocity can't go above that, right? What's our initial angular velocity, guys? 0, right? Oh, so let's see. So now the angular values I know are as follows. I know that my angular position has got to increase by 400 radians. I know my initial angular velocity is 0. I know my final angular velocity is 40 radians per second, and we're looking for time, right? Anybody see an equation we can use? That has just those variables?
The Hernandez equation.
Yeah, I would use the Hernandez equation. This guy, delta theta is 1/2 That's the angular equivalent of the Hernandez equation.
Yeah, but like, why did we name it the Hernandez equation?
It was a running joke in my class.
I was solving for
And it was nothing bad about Mr. Hernandez, it's just a thing.
only one acceleration.
No, the problem says what's the least time required. You could find the acceleration and then find the time. And doing that, you'd just be doing part B first. But so yeah, there are definitely other ways of doing this. Yes.
How do you know that it can exceed 40, the angular velocity?
Well, so are you good with this being our maximum centripetal acceleration?
No.
Okay, so the problem says the magnitude of the centripetal acceleration
Never mind, yeah, I got it.
of any point on the disk can't exceed that.
Alright. Yeah.
Cool? So then we know centripetal acceleration is omega squared r.
Yeah.
Follow? The other way you could have done it, some of you might be thinking, oh, I didn't know this equation. You certainly could have done this. You could have said, oh, well, AC is v squared over r, and solved for the corresponding velocity, and then used a jumper to find your omega. And it amounts to the same thing. Good or no? Sebo, you good?
Yes. Oh, totally good. Yeah.
All right. So once you get to here, we can solve for the time. Can I stop here, solve for the time? What's it going to give you? It's got to give you 20, so is it 20 seconds? And then you got to double it to get 40 seconds? Is that right? So this time, when you solve it, turns out to be 20 seconds. That's the time it takes to speed up,
Oh, you have to slow.
plus another 20 to slow down, so you got to double the time to get 40 seconds total. Cool? And then finding alpha, you just, use the definition of acceleration. Follow you guys? All right. So it looks like the topics that were points of concern were these ones that had centripetal acceleration. So maybe I need to make sure that I make a note of that for next year. Are we good? All right. Any other problems on the 11.1 stuff? All right, 11.2. Let's take a quick look at that. By the way, whoever asked about 16, there wasn't one. Let's see. Ooh, 21. What do we got? 4, 5, 6 people on that one. 23, 27, 28. Okay, let's talk about number 1. I guess there were only a few of you that asked about it, but it's super, super important, and it kind of gets at what Sebo was asking about before. And then if we have time, let me run through number 8. Number 8, there was some calculus going on there. So, Adam.
Time? No, it's just what? Practical joke. There's not actually. Wait, there's no 27. Cost.
It's 7. It's 7.
That's number 7.
Imagine a 2 in front of
I told you guys.
I didn't do it.
So yeah.
See, I didn't do it, so I was like, I
Are you
didn't
good or no, Adam?
I get it now.
Okay.
Gingers have like a condition for this. It's weird.
Okay.
No, I think it's just you. I didn't know that we were doing both
On the same survey, yeah. I said at the beginning, but you guys seem to have a tough time quieting down at the beginning of the hour. So I had said. All right. Okay, so I want to make sure everybody understands number 1, because to me that's like a fundamental thing, and there were, I think, 7 of you total that asked about that. So let's make sure we hit that, and then let me talk about 8, because it shows a calculus trick that I've seen show up from time to time on the AP test, and it's a thing you got to know. So this is as good a place as any to introduce it. Okay, so number 1, accelerating car. A car starts from rest and moves around a circular track with a radius of 30 meters. Its speed increases at 0.5 meters per second squared. A says, what's the magnitude of its net linear acceleration 15 seconds later? So this gets to exactly what we were just talking about. Why did I emphasize the word net acceleration? What am I trying to get at there, you guys? Or maybe we don't know.
Tangential acceleration and the centrifugal.
Good, yeah. If you've got a car traveling in a circle, it's experiencing two types of acceleration. There's the centripetal acceleration, corresponding with the change of direction, because it's going in a circle. And then there's also a tangential acceleration, because it's going faster and faster and faster and faster and faster. Okay? So, the problem tells us the tangential acceleration. What am I doing here?